now that you've done like basic types of waves and basic quantities with waves and basic calculations with speed and frequency and wavelength and all that kind of stuff, we're going to start looking at a little bit of other stuff, sort of like the wave interaction stuff that you guys have looked at as well, except we're going to look at what happens to waves in 2 dimensions instead of just 1 dimension, and how waves interact with things in 2 dimensions, not just in a straight line, but when they hit things in angles, interact with things in angles a little bit. And we're going to take care of something first, though. Suppose you are, suppose you got like a rock. Maybe you got like a rock or something like that, and then here you are on the rock. There you go, and you throw like a pebble or something like that, and here's some water. Okay, and the pebble, of course, goes into the water, makes a little splash, and of course it's going to make waves, and the waves it make would be like little circular ripples that move out. Now when we draw these guys like this, those are called wave fronts, which is what the actual waves actually look like. When we draw like the circular waves like that, those are called the wave fronts. But just drawing wave fronts sometimes can be kind of tricky. For example, suppose I draw some wave fronts like this and ask you, which way are the waves going? Are the waves going to the left or are they going to the right? Well, it's impossible to tell. But that is why we often use what's called a wave ray. So for example, if I drew something like this, you know that it is going towards the right. And that's called a wave ray. So often what we'll do, instead of drawing waves, like this is the origin here, we will draw things like this that are called wave rays, which show which way the waves are actually going. So that's called a wave ray. And these two, the wave fronts, these guys are always perpendicular to each other. So always at right angles, they're always at right angles like that. So the wave front is what the actual wave actually looks like, but the wave ray sort of makes like a vector out of it to show which way it's actually going. Using wave rays can actually show direction, and they're also a lot easier to draw. It's a lot easier to draw an arrow than drawing a whole bunch of ripples and stuff like that. So we'll often be drawing wave rays to represent wave fronts. Okay, it's just a lot easier that way. All right, but that's just a little basic fundamental type thing right there. Okay, so for example, bring up a little simulation we'll be using a little bit right now. So here, if I turn this on, there we go. All right, there's some waves traveling. Okay, so there's the wave, and the waves look like that. Try to draw that would be very, very difficult. It'd be a lot easier to draw it as a ray. It's just a line. It just makes things so much easier. Okay, so that's the basic idea behind wave fronts and wave rays. Okay, all right, so let's start looking at some of the basic things that waves do in 2 dimensions. And it's not really complicated type stuff. The first thing that we can look at is something that is really, really simple, that people know that waves do when they hit things at an angle. Of course, waves can reflect. Okay, and that's like mirrors and all that kind of stuff, really basic fundamental stuff. All right, so stuff like this. We got good old-fashioned reflection, where waves, whether they're light waves, sound waves, any kind of wave can hit a barrier and reflect off at in a different direction in 2 dimensions. And it's really simple. So suppose we have like something like suppose we got something like a mirror or something like that. So this is a nice way to think about it. Is just basic mirrors. There's my mirror. And I draw my waves coming in. Now again, so I could draw waves coming in like this, but that's just going to get complicated. It's a lot easier to draw a wave ray, which would look something like this. And of course, when it hits the mirror or the barrier, whatever it is, it's going to bounce off. And when it bounces off, it doesn't bounce off in any random direction. It bounces off in the same direction that it was before. Okay, let's see if we can match up colors here. There we go. All right. So it's going to bounce off the same direction it did before. Even on this one over here, the angle it's coming in at and the angle it's going out at are going to be the same. Now, this is where another little measurement kicks in. If we go to the surface and we go perpendicular off of the surface, this is what's called the normal. And the normal in mathematics actually means perpendicular, my little right angle there. So we have our initial angle, angle theta, theta I, and we've got theta r. I stands for incident or initial, and then theta r would be the reflected angle. And those angles are measured from the normal, not from the surface, but from the normal. So the incident angle or initial angle is going to be equal to the reflected angle or the angle afterwards. So it always bounces off at the exact same angle. So if we went over here, and there's a little mirror right here, if we drew a little line right there, perpendicular to the mirror, something like this, the angle that the light came in at and the angle it came out at would have to be identical. And that's just basic reflection, really simple. All right, so basic reflection, angle incoming, angle outgoing, those two angles are going to be the same. And how light, especially light, I mean all waves do this, but especially how light actually reflects off of materials also it's given us, like, can tell us a lot about the nature of the materials. For example, if you have something that's really, really shiny, how do you know it's shiny? How do you know it's smooth? Well, you look at the reflection. When the reflection is all nice and coherent and you can see a good reflection, you can just tell that it is nice and smooth. So, for example, I got some nice and smooth here. When the light comes in, just draw some wave rays. When they reflect off, they all reflect off all nice and they're all still parallel. So this is something, you know, this would be like a nice glossy type finish would look something like this. But if you've got something that's got like a rough finish, how do you tell? Well, when you look at something with a rough finish, there's no good image, like there's no good reflection. You can tell it doesn't reflect well. Well, that's because it's all bumpy. So even if the wave rays are all coming in nice and parallel, since the surface is all over the place, who knows, like they're going to be like reflecting all over the place and it can get all messed up, and then it just doesn't work very well. So this is sort of like a, you know, you often hear like the term matte finish or a rough finish, and you can tell purely by how well the light or whatever reflects off it. And the same thing happens with sound. Like if you have certain acoustic type rooms, they'll have either smooth surfaces or rough surfaces depending if they want the sound to reflect really well or not well. So it's used for lots of different things. Okay, but that's basic reflection. We can often actually manipulate reflection as well. For example, if you take like a curve type shape, something like this, and if you have the waves coming in, and the waves are coming in something like this, when they reflect back, they will actually reflect back and make a focal point. So right there. And this is like a parabolic shape. This is a parabola shape. And this can be used to focus things. So like even just like a satellite dish. If you look at a satellite dish, it's sort of like a round dish, but then there's like that thing that sticks out in the middle of the dish. Well, that's the receiver. So the radio waves are coming in, they're reflecting off the dish, and they're focused right on the receiver, and that's how that works. This is how sort of like how a lot of headlights work. How headlights work is sort of like the exact opposite. A lot of headlights will actually have the bulb here, and the bulb is actually shining back. And then when it shines back, it hits the surface and reflects back. It sort of makes like a wider beam coming out. So headlights work like this, spotlights work like this. Any kind of receiving dish, like if you watch like sports events and they have the guys, especially like in football, on the side of the field with that huge receiving dish and they can listen to sounds. Well, that's sort of how it works. So using reflection in different ways can be really, really, really handy. Okay, so you can actually collect and magnify waves using parabolic shapes. Okay, and that's how it works. So you can get glossy finish, you can get matte finish, you can magnify, you can do lots of different things with it. You can spread waves out, you can just focus them, you can do lots of different things. Okay, so this is all basic reflection, really, really simple. Okay, now another really, really common phenomenon out there aside from reflection is something else, and we'll look at that quickly, and that is this. And this is probably one of the first places when you're a kid, especially, you'll notice it when you're in a restaurant or something like that, and it freaks you out because your straw looks like it's broken when it's not. Now this is something else a lot of people know about. This is good old-fashioned refraction. And of course, refraction occurs, and it's more of a light thing. This is when light waves actually bend when they actually change materials. Okay, and this is what refraction is. And here's a better picture of it. You can see the light better. There you go, something like that. Light going into a piece of glass, you can definitely see the light bending. Okay, and this is more of a light thing that we can focus on. When light changes from one material to another material, it can bend if it's coming in an angle. Okay, now why does it bend? Well, let's crack up that simulation thing and I can show you why it bends. Okay, and we're going to actually show the actual waves here. So here's the waves, and they're coming in. What I'm going to do is I'm going to angle this like this. Okay, and I can actually change the angle. But I'm going to show you why it happens. I'm going to change the material in the bottom, something like that. So make a different material. And I'm hoping you can tell right here at the junction, at the border right there, what's happening to the waves. When those waves hit that other material, you can see that they're smaller. But why are they smaller? Well, they're smaller because they're getting slower. Okay, so since they slow down, they get bunched up. So like traffic, it's almost like a traffic jam. So they actually get bunched together. So let's go back here for a second. So when light changes mediums, the waves actually change their speed, and because of this, it also changes the wavelength. Okay, so let's go back to things. So how does that cause it to bend? Well, if I take this thing and angle it, it will bend. Okay, now why does it bend? Well, the reason it bends is this part right here, that part of the wave hits this first. It hits that second material first. And since it hits that second material first, it slows down and sort of gets left behind while the fast part keeps on going. So it sort of gets ahead of it. So the part that's hitting first gets sort of left behind, and the part that keeps going can sort of scoot ahead. Okay, so the waves change speed and they change wavelengths, and sort of like map things out a little bit here. Okay, so when that wave comes in, I'm just going to draw very similar, something like this. Okay, does this, something like that. I know it's kind of at best wrong, but when it hits that second material down here, it actually slows down. Okay, and this part right here, this part here, that part is sort of left behind. Okay, not really, but it's sort of left behind, and that's what causes it to change direction. So since it's left behind, because this is the part that is actually slower, that's what actually causes it to change direction. So it slows down in the second material, and that causes an overall direction change. Okay, and this is how refraction works. So we're going to be looking at this in more detail and that type of stuff. That's the basic idea. Okay, so when it changes materials, get that thing going again. There you go. Okay, so it changes speeds. It gets bunched up. The wavelengths become smaller. And as you angle it, this part right there, okay, the part that hits first gets sort of left behind, and that part sort of whips around a little. It's almost like whipping it around, and it changes the overall direction. And the bigger the angle, the bigger the change in direction. You can see a little bit of reflection going as well. Okay, that's actually partial reflection. Okay, so that's why it actually bends. All right, so it's a little bit tricky-ish, but it's not too bad. Okay, but that's why light bends when you change mediums, is because it slows down. All right, so this is where the faster ones were, slows down. So it slows down in the second material. It causes an overall direction change, and also the wavelength also got smaller. Okay, so the wave slows down, it changes direction, sort of gets held back, while the other part just keeps on going the same speed, and that's what causes refraction. And we'll look at this into quite a bit more detail, probably in the next video.